Greetings, chemists. I'm really excited about today's lesson because not only am I going to address ionization energy, which is a very important feature of different elements, and it's related to their atomic structure, but also we're going to talk on a general level about how to use the periodic table to your advantage when you're making predictions about the ways that different elements behave in bonding and in situations where there are other attractions in their, I guess you could say, their atmosphere. This particular lesson is about ionization energy, and we want to figure out the periodic trend. I'm going to be very slow and deliberate. This might be a slightly longer lesson, all right? But you can use this lesson for not only day 12 of unit 5 on periodicity, you can use it for previous days and subsequent days. So in previous days, you discussed electronegativity. In subsequent days, you'll discuss another feature called atomic radius. And I'm going to talk about how all three of those things are going to be related and how we can observe them on the periodic table. So when we say a periodic trend, first of all, what we're talking about is a trend with respect to the periodic table. We're going to take a look at both the periodic table and table S, okay, which is closely aligned in our reference table. And those two can be the key to unlocking so many properties of different elements. But first of all, what is it that we mean when we say ionization energy? All right, in this lesson, you need to be able to define ionization energy, and then you can determine the ionization energy by looking at the reference table. And you can also predict the relative ionization energy of certain elements by looking at the periodic table. And that's going to lead us into the periodic trend with respect to ionization energy. Okay. And so as they define it here, ionization energy is the energy required to remove an electron from a specific atom. Now, first of all, if we recall from early on in the chemistry course, an ion is an atom with an unequal amount of protons and electrons, resulting in an overall charge, okay? And just to be brief, what I'm gonna do is I'm gonna draw a simple model of a hydrogen atom, all right? So we know hydrogen, it will have one proton in its nucleus and one neutron, all right? So 1p, one neutron, and then it's gonna have a single energy level. I'm gonna put that in blue. I have a single energy level outside orbiting with one electron. All right, and I'm gonna put that electron in green, okay? So that is our 1e. I'm going to write a negative sign just to remind you that electrons are negatively charged, protons are positively charged, all right? Neutrons have no charge, they are neutral, but they add mass, okay? So the brilliance of our modern periodic table, not the first iteration, the Mendeleev periodic table. The Mendeleev periodic table was organized by atomic mass, so things were slightly off at times because we had different isotopes, meaning different versions of an element with different amounts of neutrons, okay? And since neutrons are so much more massive than protons and electrons, all right, they could seriously affect the weight, and that would mean that he misplaced a few elements here and there. And that seriously disrupted our understanding of elements' different characteristics. Now, our modern periodic table organizes the elements with respect to how many protons they have. In other words, their atomic number, okay? And the final thing that I'm going to say about basic atomic structure, and hopefully we remember this, is that the nucleus is where protons and neutrons are contained. It is that dense middle, very small, okay, where those positive charges and those neutral charges reside. Mostly the atom is made up of empty space, and we have these electrons orbiting at different energy levels, and that's what we call the Bohr model of the atom, okay? And so when we talk about an ion, and we talk about unequal amounts of protons and electrons, since the electrons are outside, they are the ones that are attracted to forming bonds and either pulling in more electrons based on the amount of valence electrons or electrons in the outer shell, or letting go of electrons, again, based on how many they have. If they actually transfer those electrons to another element, we say that an ionic bond has happened, and that is between a metal and a nonmetal. If the electrons are shared between two nonmetals, then we are talking about a covalent bond, all right? And then we draw what we call a molecular structure to describe that covalent bond. Hopefully all of that review makes sense. The ionization energy is the amount of energy required to remove an electron. And hopefully we can see here, and I'm going to zoom in a little bit. Let me present this screen. Okay, so if we look here, as we go across, sorry, I'm going to go back one slide. As we go across a row, it's described here in table S of the periodic table in a column, all right? As we go from 1 to 5, that is actually a row, all right? 1 and 2 are a row unto themselves, and then we go down and we have 3, 4, and 5 on the next row. As we go from 3, 4, 5 all the way over to 10, which is neon, all right? Everything from here to here, we're going across one row. This is a different row. I'm going to mark it with a different color. Okay, so 1 and 2 have their own row. 3 to 10 have another row. And we can see what's happening as we go from 3 to 10 is that the ionization energy is increasing. So it takes more and more energy as we go across a row to remove an electron from an orbital, all right? And so let's look at a graph of what that looks like, and then I'm going to explain the logic behind it. So if we look at this, we can see this first point that I'm circling here, that's hydrogen. And there's a jump in ionization energy as we get to helium. Then it goes really low as we get to element 3, and it goes all the way back up as we go through element 10, which is neon. Okay, so that's 10, that is 3, and so on and so forth. Every time we start at the beginning of a row, I'm going to circle those in blue because they have very low ionization energy. Okay, and so on and so forth. As we get to the end, I'm going to circle those in orange. Those elements have very high ionization energy. And the reason why it becomes more and more difficult is because over the course of this journey from here to here, let me actually mark that, undo, let me mark that in green. As you go from here to here, or here to here, etc., what's happening is the valence shell, or the outer shell, the valence shell fills up. Okay, when we get to krypton, we jump to the next element after that, we are adding 1 to a new shell. All right, and now let's think about what each atom really wants to happen. It wants to achieve stability. And if you recall from previous videos of mine, stability is achieved by meeting the Octet Rule, which says that elements, or atoms of elements, want to have 8 valence electrons in their outer shells, with the sole exceptions being hydrogen and helium, because they only have 1 valence shell, which means they want to have 2 in their outer shells. Okay, and so the closer they get to 8, the more they want to hold on to what they have and add more. The farther away from 8, the more likely they are to let go of what they have in order to get stability by moving in the reverse direction. So for example, an element over here is 1 shy of having a full valence shell. Okay, so it really wants to get to xenon's electron configuration. Okay, and it's unlikely to give up the 7 electrons that it has in its outer shell. It's much more likely to try to pull 1 more in. So it takes a lot of ionization energy to remove an electron from this configuration. Okay, and so let's look at what this looks like in the periodic table. All right, and so over here you can see what I was talking about with 2 through 10, or 3 through 10. All right, and I'm going to describe that with an arrow going from left to right. We have lithium all the way to neon. We are adding electrons to the valence shell. and that's increasing the ionization energy. Okay, and so in each row it'll increase. Once we get back to the beginning, it will jump back down again, and it takes a lot more, or sorry, a lot less energy, for example, to remove an electron from sodium than it does from, say, neon or fluorine. As you can see, fluorine has 7. I'm sorry, it's really tiny there, but it has 7 valence electrons. Neon has 8. I'm just going to write VE for valence electrons. All right. Sodium only has 1. All right, because it filled that shell, so its configuration is 2-8-1. So it only has 1 electron. So it's a very low ionization energy. It will give up that electron very easily. And we know this from table salt, which is sodium chloride. It will give up an electron and transfer it to the chlorine, which, like fluorine, has 7 in its outer shell. So across a period, as we say, when we're describing going across a row, ionization energy will increase. Now let's look at what happens as we go down a group. So to go down a group is to go vertically down on the periodic table. All right, and as we go down a group, we're increasing the amount of shells. So to depict down a group, I'm going to draw potassium, and this is going to get us into a discussion of what happens as we have more and more shells and the relative energy it would take to pull out electrons. So I've got 4 shells here with potassium. Potassium is K. All right, so you can see it right here. I'm going to circle it. Let me change this. I'm going to circle it in red. That's potassium 2-8-8-1. That means that in our first shell, we got 2. And then in our next shell, we've got 8. 1, 2, 3, 4, 5, 6, 7, 8. And then in our third, we've got 1, 2, 3, 4, 5, 6, 7, 8 again. All right, and I need one more. So I'm gonna add a 4th shell. And in that 4th shell, we have 1. I'm going to make it a little bit larger so we can really see this difference. Now, if you're thinking about why it's easier as we go down, all right, if we compare sodium, sodium has the same electron configuration, -1 full shell. Sodium's electron configuration is 2-8-1, while potassium's is 2-8-8-1. All right, and now whereas with sodium, we would be talking about this electron here being the only one in the 3rd shell. Now the 3rd shell is filled and we've got the 4th shell. Now the way I've drawn this is for simplicity's sake, but in reality, our nucleus is tiny. It looks like that size, okay? And so this 4th shell lone electron over here is very far away, okay? Because it's so far away, it will take less and less energy the farther away it gets from the nucleus to pull it away from that atom. Okay, so by the time we're down to francium, which is atomic number 87, you can see it back down there, it's going to take very little energy to pull the lone electron from its outer shell. It's going to take more energy to pull sodiums or potassiums or lithiums. It will take the most because that only has 2 valence shells. Hydrogens, it will take very little as well because that only has a single valence shell with 1 electron. Okay, so the farther away we get, the more shells we add in between, the less energy it will take to pull a valence electron. Now, the other thing I want to say about this is we call this one a valence electron because it's in an outer shell. However, we call all of these inner shell electrons. You could also call them inner kernel electrons. Now, these are closer and closer to the nucleus. So the principle at work here is that valence electrons are much easier to pull from an atom than inner shell electrons. In other words, valence electrons take less ionization energy, right? And hopefully that illustration shows you why. It's almost like there's this pull between the nucleus and the electrons, but the farther and farther away those electrons get, the weaker the pull is, okay? So one more time to go through it. As we go across a row, our ionization energy is increasing because they're getting more and more electrons and they want to keep what they have. But down a group, we're adding more and more shells in between our innermost shell and our nucleus on the one hand, and our valence shell, which is our outermost shell. And the more shells we add, the weaker the grip the nucleus has on that valence electron. Now, just to go over trends, we know also something else is increasing, all right? If we go back to table S, which is our other very valuable table to check this stuff out on, all right, we can see that as we go from 3 to 10, I'm going to put an arrow here. We go from 3 to 10, our electronegativity is also increasing, all right? Finally, as we go from 3 to 10, our atomic radius is decreasing. And now let me describe why these two things happen across a period. So across a period, as we said, we're adding more electrons, which means it takes more energy to remove any one of them because that atom wants to get to the octet really badly. And the closer it gets, the more unwilling it is to give up what it already has. And electronegativity is a measure of how attracted that atom is to other electrons. So the more it gets close to that octet, the more it wants more. So electronegativity is also going to rise. In other words, ionization energy and electronegativity increase across a period. All right. Also, ionization energy and electronegativity decrease down a group, right? And the reason they both decrease down a group, I've talked about ionization energy already. It will take less energy to pull an electron, the more shells we add in between it and the nucleus. So as we go down a group, we add more electron shells that are filled. That means there's kind of a buffer, okay? And the outermost electrons are more weakly held by the nucleus. Also, the more we go down, the less kind of an impulse that atom has to pull in more electrons. So even though an atom in, say, the 4th or 5th row still might only have 1 or 2 valence electrons in the outer shell, it will still want more. But if we go up to the 2nd row or the 1st row or the 3rd row, those will want an electron more because they are a little bit more greedy for them, all right? The other ones already have many filled shells, and you can think about it that way. You can think the more filled shells that they already have, the less kind of impulse they have to pull in an electron, all right? And so they will be less electronegative, and we can see that trend happening as we go from 11 to 18. I'm going to make an arrow here. If we go from 11 to 18, we can see again across the group, all right, or sorry, across the period, our electronegativity is increasing, but all of these numbers, I'm going to circle them, all of these numbers are lower than their counterparts 1 period above, okay? All of those are higher than their corresponding counterparts, all right? And so we can see as we go down a group, the electronegativity is going to decrease proportionally, all right? Now, atomic radius, on the other hand, as you can see, is going to increase as we go down a group. So both of its trends are opposite that of electronegativity and first ionization energy, all right? So if I make another arrow here to illustrate, we can see here atomic radius is increasing and it's much, much bigger. So one row down, all right, as we go down a group, we go 1 row down, we can see that these numbers, all of these numbers, are proportionally larger than all these numbers in 3 through 10. The reason why the atomic radius increases so much, well, I have a whole full shell of inner electrons in between that and the outermost shell. And our atomic radius is a measure from the middle of the nucleus to the average distance out to our outermost shell or outermost electrons. So obviously, if I stack more shells in between, my atomic radius is going to get bigger and bigger, all right? And so that's why all these proportionally are larger. However, within this, all right, we can see, and I shouldn't have circled potassium because that gets into the following row, but we can see, let me undo that. From here to here, our final trend that I want to illustrate is that within a period, from here to here, within a period, we can see that atomic radius decreases, all right? So I'm going to write that in a text box. That's our final atomic radius. Say it, 1 down a group, it increases because there are more shells between the nucleus and outermost shell. Okay, across a period, it decreases. And let me tell you about what's happening there. As we add more electrons, all right, like we said, if we add more electrons, the tendency of the atom is to want more. The electronegativity goes up, and it really wants to hold on to what it has. And as it's holding on to what it has, it's going to pull it tighter and tighter. So the more electrons we add in the outer shell, the tighter they're going to be pulled in. So we see this small decrease happening, as you can see here at element 11, sodium, to element 18, argon. Our atomic radius is decreasing from 160 picometers down to 101 picometers, all right? And so bottom line, overall, ionization and electronegativity share the same trends. They increase across a period, they decrease down a group. On the other hand, atomic radius, down a group, it will increase, but across a period, it will decrease. The bottom line of all of this, periodic trends are super valuable when it comes to evaluating the tendencies of different elements. This unit is all about examining the different groups and understanding their behaviors with respect to the periodic table. So all the elements in group 1, they tend to share certain characteristics, as do all the halogens, which is group 17, as do all the noble gases, which is 18, and so on and so forth. Every group is going to tell you a clear picture of what the elements inside of it, what their tendencies are. And as we read across a period, we can compare elements relatively based on how close they are to the right or the left, all right? And so moving forward, as you evaluate the tendencies of different elements, don't forget about the periodic table, don't forget about electronegativity, don't forget about atomic radius, and don't forget about ionization energy. I hope this has been valuable to you. As you examine these, make sure that you try Regents questions in order to test your understanding of these, and I will see you soon.